Have you ever looked up at the night sky and seen a giant, bright planet? That might have been Jupiter. Jupiter is the biggest planet in our solar system. It's a gas giant, which means it's mostly made of swirling gases like hydrogen and helium. It's so big that all the other planets could fit inside it. This massive planet is known for its great red spot, a storm that has been raging for hundreds of years. But Jupiter has another, even more spectacular feature. At its north and south poles, Jupiter has the most powerful and beautiful auroras in our entire solar system. These are like the northern lights on Earth, but on a much, much grander scale. So, what exactly are these amazing light shows? To understand auroras, we first need to talk about something called plasma. Plasma is often called the fourth state of matter, after solids, liquids, and gases. Imagine you heat up a gas so much that its atoms break apart. The tiny particles inside, called electrons and ions, start zipping around freely. That super-energized, electrically charged gas is plasma. The sun is a giant ball of plasma, and it's constantly sending out a stream of these charged particles, which we call the solar wind. Auroras happen when these energetic particles from the sun get trapped in a planet's magnetic field and then slam into the gases in its atmosphere. When these high-energy particles collide with the atmospheric gases, they give the gas atoms a big boost of energy. But the atoms can't hold on to that extra energy for long. They quickly release it in the form of tiny packets of light, called photons. It's this release of light that creates the beautiful, dancing curtains of an aurora. On Earth, we see this as the aurora borealis and aurora australis. On Jupiter, this same process creates a light show that is hundreds of times more powerful and larger than our entire planet. It's a truly cosmic spectacle, a vibrant dance of light happening millions of miles away. This process is driven by a planet's magnetic field, which acts like a giant invisible shield. The magnetic field funnels the charged particles from the solar wind toward the planet's poles. Think of it like a giant magnet guiding tiny metal filings. Jupiter has the strongest magnetic field of any planet in our solar system. It's almost 20,000 times stronger than Earth's. This incredibly strong magnetic field is the reason why Jupiter's auroras are so intense and permanent. Unlike Earth's auroras, which flicker on and off depending on solar activity, Jupiter's auroras are always there, a constant glowing crown on a giant king. While the basic recipe for auroras is the same, Jupiter and Earth cook up their light shows very differently. Here on Earth, our auroras are famous for their beautiful shades of green and pink. These colors come from charged particles hitting oxygen and nitrogen atoms in our atmosphere. The green lights are created by oxygen at lower altitudes, while the rarer pink and red hues come from nitrogen and high-altitude oxygen. To see them, you usually need to be near the Arctic or Antarctic circles on a very dark night. They are a special treat, often appearing and disappearing based on the strength of the solar wind. Jupiter's auroras, on the other hand, are a whole different beast. Because its atmosphere is mostly hydrogen, its auroras glow in colors our eyes can't normally see, like ultraviolet and X-rays. Scientists use special telescopes and cameras to view these invisible light shows. If we could see them, they would likely appear as brilliant shades of blue and pink. And you wouldn't need a dark night to see them. They are a permanent feature. Another big difference is that while Earth's auroras are mostly powered by the solar wind, Jupiter generates a lot of its own aurora-making particles from its volcanic moon, Io, which spews sulfur and oxygen into space. The sheer size and power of Jupiter's auroras are mind-boggling. Earth's auroras are beautiful curtains of light, but Jupiter's auroral ovals are larger than our entire planet. They release so much energy that if we could somehow harness it, it would be enough to power all of human civilization for a very long time. This immense energy creates a very extreme environment. The plasma zipping around in Jupiter's magnetosphere is incredibly hot and moves at unbelievable speeds. It is one of the most dynamic and chaotic places in our solar system, making it a perfect laboratory for studying how plasma behaves under extreme conditions. The source of the auroras also highlights a key difference. Earth is a rocky planet with a relatively simple magnetic field, and its auroras are almost entirely a result of its interaction with the sun. Jupiter, being a gas giant, spins incredibly fast. A day on Jupiter is less than 10 hours long. This rapid rotation, combined with its metallic hydrogen core, creates its monster magnetic field. This field is so large it would appear bigger than the full moon in our night sky if we could see it. This complex system, fed by both the sun and its own moon Io, makes Jupiter's auroras a uniquely complex and fascinating phenomenon to study. To get a closer look at these mysterious auroras, NASA sent a special explorer to Jupiter. This mission is called Juno. Launched in 2011, Juno is a spacecraft designed to orbit Jupiter in a very special way. Instead of circling the equator like many other probes, Juno flies in a long, looping path that takes it directly over Jupiter's north and south poles. This polar orbit is perfect for studying the auroras up close. Juno is built like a tank to survive the intense radiation belts around Jupiter. Its sensitive scientific instruments are protected inside a titanium vault to keep them safe as it dives through the most dangerous parts of Jupiter's environment. During its daring flybys, Juno swoops just a few thousand kilometers above the swirling cloud tops, closer than any spacecraft has ever been. As it passes over the poles, it flies directly through the regions where the auroras are born. It's like flying right through the curtains of a light show. Juno is equipped with a suite of amazing tools that can listen to the magnetic and electric fields. One of these instruments, called waves, is designed to measure radio and plasma waves. By listening to these invisible waves, scientists can understand how the particles that create the auroras are being energized and accelerated down into Jupiter's atmosphere. On a recent pass over the poles, Juno's Waves instrument detected something completely new and super exciting. It picked up signals from a type of plasma wave that scientists had never seen before at Jupiter. These newly discovered waves are called quasi-periodic waves, and they have a very, very low frequency. Imagine them as a deep, slow bass note in the cosmic symphony of Jupiter's plasma. These waves are thought to play a crucial role in a process called magnetic reconnection, where magnetic field lines snap and reconfigure, releasing huge bursts of energy. This is one of the key processes that can help fling particles into the atmosphere to create auroras. This discovery was a big surprise. Scientists have theories about how Jupiter's auroras work, but finding these specific waves provides a new piece of the puzzle. It suggests that the processes happening in Jupiter's giant magnetosphere might be even more complex and varied than we imagined. These low-frequency waves seem to be a key ingredient in the recipe for Jupiter's powerful auroras, helping to explain how particles get shot down with such incredible force. It's a fantastic discovery that is only possible because of Juno's unique ability to fly right through the heart of the action, giving us an insider's view of this alien light show. You might be wondering, why should we care about plasma waves on a planet that's over 600 million kilometers away? Well, studying Jupiter's extreme environment is like looking at a supersized version of processes that happen right here in our own cosmic neighborhood. Earth also has a magnetic field that protects us from the solar wind. This shield is incredibly important. Without it, the constant stream of harmful radiation from the sun would strip away our atmosphere, making life on Earth impossible. Learning how Jupiter's massive magnetic field handles an even more intense barrage of particles gives us valuable insights into how our own shield works. The same physics that governs Jupiter's auroras is also at play in the space around Earth. The sun can sometimes unleash powerful solar storms, which send massive clouds of plasma hurtling toward us. When these storms hit Earth's magnetic field, they can cause problems for our technology. They can disrupt GPS signals, damage satellites in orbit, and even cause power outages on the ground. This is often called space weather. By studying the intense and predictable space weather at Jupiter, scientists can better understand the fundamental physics of plasma and magnetic fields. This knowledge helps us improve our models for predicting space weather here at Earth. This new discovery of quasi-periodic waves at Jupiter is particularly important. It gives us a new clue about how magnetic reconnection works in a real-world setting. This process doesn't just create auroras, it's a fundamental force across the universe, happening in the sun's atmosphere and in distant galaxies. Understanding it better helps us protect our astronauts and our technology. Better space weather forecasts can give satellite operators time to put their spacecraft into a safe mode and help power grid managers prepare for potential impacts. In a way, Jupiter is acting as our giant, distant laboratory for planetary protection. Ultimately, every new discovery like this expands our understanding of the universe. It reminds us that there is still so much we don't know and so much left to explore. The findings from the Juno mission are not just about Jupiter. They are about the universal laws of physics that connect everything, from the smallest atom to the largest planet. This knowledge will be crucial for future space missions, whether we're sending humans back to the moon, to Mars, or beyond. By unraveling the secrets of Jupiter's alien auroras, we are taking another small but important step in our grand journey of cosmic exploration.